Let's talk about electric cars. You've got this giant DC battery pack, right? But the motor it's driving is this super sophisticated AC machine. How does that even work? They're basically two different languages of electricity. Well, it turns out there's a brilliant piece of engineering that acts as the translator. And today, we're going to pull back the curtain on the clever trick that makes it all happen. So here's the fundamental problem we need to solve. Your battery gives you a nice, steady, flat line of DC power. Simple. But a high-performance motor? Oh, it needs three perfectly timed, beautiful AC sine waves, all dancing around each other. So how do you get from A to B? The answer lies in a little box that's both incredibly simple on the outside and wonderfully complex on the inside. And here it is, the hero of our story, the three-phase inverter. Its whole job in life is to take that boring DC voltage and, with some ridiculously fast and precise electronic switches, chop it up and basically stitch it back together into three-phase AC power. It's the ultimate go-between. But, the moment you decide to build one, you're faced with a choice. Right away, engineers hit this fork in the road. There are two basic ways you can physically build one of these things, and the choice between them is a classic engineering story. The first path you could take involves, well, a lot of parts. We are talking 12 high-power electronic switches. It's the most direct way to think about the problem, but it's also the most complicated. You can really think of this as the brute force method. It's like, hey, we need 3 AC waves, so let's just build 3 completely separate inverters and stick them together. Now, this actually gets used in some really high-end specialized systems like a megawatt-scale research project at MIT that powers these custom-built motors. But for pretty much every electric car or industrial motor out there, this is just way overkill. There's a much, much smarter way. And that smarter way, well, it cuts the number of switches clean in half, down to just 6. And that simple change has huge implications for everything: cost, size, reliability, you name it. So on one hand, you've got the 12-switch design. It's powerful, sure, but it needs a special kind of motor. On the other hand, you have the 6-switch design. It's this elegant, integrated bridge that works with all the standard motors that are everywhere. It's simpler, very fewer parts to break, and it's more efficient. That's why it's the undisputed champion. This is the design you'd find if you cracked open the inverter from a Toyota Prius. Okay, so we've made our choice. We're going with the elegant 6-switch design. But here's the thing. Having the hardware is only half the battle. The real magic, the part that's actually tricky, is figuring out how to control those 6 switches. How do you choreograph them to turn on and off thousands of times a second to create a perfect, smooth AC wave? Well, there are 2 main schools of thought here. First, there's something called 6-step control. It's simple, it's easy, and it squeezes every last drop of voltage out of your system. But the wave it makes is kind of ugly. It looks more like a staircase than a smooth wave, and it's full of electrical noise. Then you have pulse width modulation, or PWM. This is way more sophisticated. It creates a beautiful, pure sine wave, but the trade-off is you can't get quite as much maximum voltage out of it. We're going to focus on PWM because, really, its precision is the secret sauce to modern electric motors. It's what gives an EV that incredible, smooth, silent feeling off the line. The whole idea is kind of brilliant. By turning the DC voltage on and off super, super fast, you can control what its average value is. And you can make that average trace out a perfect sine wave. So how's it work? Think of it like a recipe. You start with 2 signals. First, a really fast triangle wave. That's kind of like your metronome, just ticking away. Second, you have the perfect sine wave you want to create. That's your reference, your goal. You feed both of these into a little circuit called a comparator. And it's simple. Whenever the sine wave is higher than the triangle wave, the switch is on. Whenever it's lower, the switch is off. The result is this machine gun burst of DC pulses that, on average, look exactly like your target sine wave. It's amazing. Okay, this brings us to a super important idea, the modulation index, usually just called M. Think of it as a volume knob for your inverter that goes from 0 to 1. An M of 1 means your reference sine wave is as big as it can possibly be without getting distorted. You're using 100% of your clean voltage. But what happens when the motor needs to spin faster? It demands more voltage. What happens if you try to turn the knob to 1.1? Well, the top and bottom of your beautiful sine wave get chopped off. You're creating distortion. You've hit a hard wall. So we're stuck. To go faster, a motor needs more voltage. But our best, cleanest control method, PWM, hits a hard limit. We need more of that fundamental voltage, but we can't get it without messing up the waveform. This is the exact moment an electric car would just stop accelerating. So what if there was a sneaky way around this limit? This is the million-dollar question for an engineer. How do you squeeze another 15% of performance out of the exact same hardware? It sounds impossible, right? You can't just create voltage out of nothing. But what if you could play a little trick with the shape of the wave? And this is it. This is the aha moment. It's a technique called third harmonic injection, and it is so wonderfully counterintuitive. Instead of starting with a perfect sine wave, you actually add a tiny little bit of a specific kind of distortion. When you add this third harmonic, the combined wave gets a flatter top. And because its peak is now lower, you can make the whole thing bigger. You can turn up the main fundamental sine wave by about 15% before this new flat top hits that ceiling. You're getting more of the good stuff by cleverly adding a little bit of the bad stuff. Okay, I know what you're thinking. Wait a second, you just added distortion on purpose? Isn't that going to make the motor vibrate and get hot? That's the obvious question. And the answer is what makes this trick so incredibly cool. So here's the secret. You add that exact same third harmonic distortion to all three phases. Phase A gets it, phase B gets it, and phase C gets it. And because of the way the math works out, these three little distortion waves end up being perfectly in sync with each other, what engineers call in phase. And this is where the magic happens. A three-phase motor doesn't actually feel the voltage on any single wire. What it feels is the difference in voltage between the wires, what's called the line-to-line voltage. So when the motor looks at the difference between phase A and phase B, those two identical third harmonic distortions get subtracted from each other, and poof, they completely disappear. They were just a ghost in the machine, a tool you use to get more headroom for the real wave that the motor actually feels. Now, this whole trick is really just one point on a whole spectrum of choices. In the real world, engineers are constantly making decisions balancing this trade-off between getting perfect performance and getting maximum performance. You can kind of see the menu of options here. You've got your standard PWM that gives you the absolute cleanest, purest waveform, but you're stuck at 100% of your base voltage. Then there's our clever trick, third harmonic injection. That gets you a free 15% voltage boost, and it's still super clean from the motor's point of view. And then, if you just need every last bit of power, you can just push the inverter into overmodulation. You basically just floor it. That'll get you the absolute most voltage, almost 127%, but it comes at a cost. You start introducing other nastier harmonics that can make the motor noisy. And this isn't just some textbook theory. There was a paper from Toyota engineers talking about the inverter in the Prius, and they basically said, look, when we needed the car to go faster, we ran out of clean voltage, so we just let it saturate. We let it create those harmonics. And you know what? The motor handled it just fine, and the car went faster. It's a perfect real-world example of choosing practical performance over theoretical perfection. So, after all that, what's the big idea? Let's wrap this up with the one thing you should really remember. The huge takeaway here is that so much of great engineering isn't really about building something that's flawless. It's about deeply understanding the limitations and the imperfections of your system, and then finding these clever, sometimes totally counterintuitive ways to manage them or even use them to your advantage. It's not about getting rid of the impurity. It's about using it to get a better result. And that really leaves you with a final thought, doesn't it? This whole idea of trading a little bit of purity to get a lot more power, it's everywhere. It's in the way your MP3s are compressed. It's in how your car's engine is tuned. So the next time you see a piece of tech that's just performing at its absolute limit, ask yourself, what imperfection are they cleverly bending to their will to make that happen?